Good morning, students. For the today's session, we'll be seeing the tracking. Previously, we see the concept of synchronizing. There, we have seen the concept called parallel search, serial search, acquisitions. So, coming from that, we have seen a specific formula related to that, and we have seen the direct sequence plus spectrum and frequency popping plus spectrum. The two perspective point of view where parallel search and serial search acquisition is being we've been used in the receiver side to make sure the clock are being synchronized together and the sequence be generated uh, correctly. So here uh, in tracking, okay. So we will see the process of concept called tracking. So tracking signals here emphasis on the receiver side after acquisition, we go for tracking. So once acquisition or core synchronization, okay. So once acquisition based on parallel or serial and based on course synchronization is completed, tracking or fine synchronization take place. So there is a coarse synchronization, there is a fine synchronization. So acquisition part is a core synchronization, okay, and the tracking is also called as a fine synchronization. Uh, Synchronization. So here, previously acquisition we have acquired the code sequence and based off some sequence form with respect to some time period we have taken and previously we see in the we have saw some parameter like lambda, EC, okay, code duration and some chip lambda. So according to that, we try to reframe the bits based on the course synchronization, where in tracking we'll be having a very good refined synchronization bit done. So tracking code loop can be classified as here also as coherent and non-coherent. So here the is a looping process. So coherent loop is one which is the carrier frequency and phase are known exactly. So the loop can operate on a baseband signal. So let us take PPSK or any kind of baseband signal. In a coherent loop, there is the carrier frequency and phase are known exactly. So in non-coherent loop, where the carrier frequency is not exactly known because due to some Doppler effect or nor is the phase. So there is a in the non-coherent the frequency phase are not being known exactly. So either mode we can put it to either you design based on coherent loop or non-coherent loop. So in most circumstances, like the carrier frequency and phase are not known exactly. So as a prior, a non-coherent code loop is used to track the received PN sequence. So here the tracking we use the non-coherent code loop to track the received PN sequence. So the tracking loop is further classified based on full-time uh, early late tracking loop, a full-time early late tracking loop, and often referred to as a DLL delay log loop, or a time shared early late tracking loop is called as a tau dither loop TDL. So basically, the tracking loop section consists of two sections: one is DLL and TDL. This DLL based on delay based and tau dither based on dithering of signal. So you'll see that what is that exactly means. So here DLL based DSS signal tracking DSS signal. So here we have an input sequence, okay, a of root of p x of t g of t and cos parameter. So this is like a delay sequence with respect to property of detection. Okay, we have some omega naught is 2 pi f. Okay, so 2 pi f naught. PF5 is the phase. This signal has been given to this detector. Early correlator it correlates with the PN support sequence. Okay, early correlator and late correlator is there. So here you have a sequence T minus TC by 2 is a half chip time. Okay, tau is time period and TC total tau is delay and T is time period. So desplitting. So there one portion of signal is going to it's been desplitted. Okay, and it's also been paired sequence generation may also be given with a different polynomial function g of t plus tau. And this, if you take this g of t, t minus t, and this all three g of t sequence is been given at a different sequence level. So here one portion is given to data demodulator, one portion is given bandpass filtering, one portion is given as bandpass filtering. So, okay, so it's all is combined to a square law detector. So combines a square law detector and summate all the sequence. It is y of tau, and there is a filtering when applied. There is a VCO voltage controlled oscillator. They are superimposing the signal with the oscillator signal. This is a the finite oscillator, and it is further it has been given to the PN sequence generator. It is a loop, so it goes on like looping out and tracing tracking the sequence in a correct manner. So until it gets it, it goes on makes a looping out, and after that it is after that it all correlated and the data demodulated and data output is being given. So ultimately there's a delay being governed here g plus tau, and the tau delay has been given. This the splitting is based on the delay. So you will be seeing that how tracking being done with respect to some different delay element. So if you let us take a spectrum binary BPSK signal. So BPSK signal, the data x of t, and the code is g of t. Okay. So the equation can be written. Okay, R of t is equal to a root of 2p x of t g of t cos omega t plus phi. So here this defines the uh, constant. A is a constant. It defines the gain parameter, that is the system gain, and phi is the phase angle. We call it as random phase angle in the range of 0 to 2 pi radians. And the locally generated code of the tracking loop is in phase with the g of t, incoming g of t. So the from the locally generated tracking loop signal is will be an offset in phase with the g of t. So by the time tau, so tau should be less than tc by 2. That's one condition for fine synchronization. So for previously we got a core synchronization for adaptation. So for the fine synchronization, the G of T code, G of T code is being delayed from each other by one chip. So it is delayed by each other by a one chip. So you can see there TC by 2. That's a chip duration of chip plus tau. That's a tau can be taken as another chip term. So altogether it is one chip. So the two bandpass filters are there in the diagram are being designed to pass the data. So you can see here there are two bandpass filters. So it is mainly designed or been added to the design to pass the data and to average the product of G of t and the two PN sequence. There is a two PN sequence coming from, okay, and there is a one from here, early correlator, late correlator, and they are going to pass the data. It's going to pass the data averaged. That's the main thing. So there is a filtering being done, and there is a passing of data with an average of G of t. So the square law envelope detector next that estimates the data since mod of x of t is equal to 1. Okay, so it eliminates the data if x of t is equal to 1. So x of t is the data. So you should have a sequence of data in that. So the output of each envelope detector is approximately called as ED suffix D. E is the expected value. E is the expected value, which is you can see on the this equation. E of D, E is the expected value, how much value you're going to get. So E of inside the bracket, it means expected value, and RG of uh, RG of x is equal to that you get RG mod of RG tau plus or minus TC by 2, where RG is an autocorrelation function of the PN sequence. So the feedback signal y of t, y of tau, one of the signal being coming from this diagram, this y of tau, okay, is being given to the PN sequence. When tau t is positive, the feedback signal y of tau instruct the VCO to increase its frequency. Okay, so when the tau is positive, it says the y of t tau signal to be it instructs the VCO to increase the frequency, and thereby it tries to force tau to decrease. So that's one condition. Tau is positive. It will instruct the VCO to increase the frequency, causing the tau to decrease. And when the tau is negative, y of t instruct the VCO to decrease, and thereby forcing tau to increase. So it's just like inversely proportional to each other with the tau and the frequency. And tau is nothing but is a time, so it should be less than TC by 2 for the incoming m of t. When the tau is to be small number, it is g of t, okay, and g of t plus the approximate 1. If you take approximate 1, yielding the it gives the t splitting of signal z of t, okay, which is applied to the conventional demodulators. So here, this diagram, so it makes sure this y of t is having a relationship with VCO to give a higher frequency or a lower frequency, and the tau increased or decreased. So this will make sure the splitting is been happening, and tracing being done with respect to this fixed voltage control oscillator, that the data output sequence has been tracked properly with no kind of alter in this data. So that's the one thing which you use in DSS. Next one is a frequency FSS. We use this tau dither generator. So we will see this tau dither loop. So the problem is some control loop is like the loop is tracked accurately. When the loop signal is 0, the loop get confused. So when the loop signal, when it is having a 0 value, so the loop get confused. Always gives an errant values like it always gives a continuous 000. So it can confuse sometimes. So the due to some lagging in the tracking process, okay, some control loops can get away from this signal. So this is especially in the case of tracking loops that modify the own loop gain, that is in response to the perceived environment. So it tries to modify its loop gain A constantly such a way that output data gets an errant, a different kind of data sequence. So here we use this tracking, time shared tracking, which is called as tau dither loop, okay, which is to deal with the potential problem of this problem by injecting a small error in the tracking correction. So you're going to insert a small error function such a way that it will solve those zero error. So the looping vibrates continuously with the correct answer. Okay, so the vibration is very if the vibration of the looping is small, the loss will be minimal. So if goes on looping happens for n number of times and not able to find, so there is a problem. So this design will tackle that problem by introducing a uh, correction code. So this vibration is typically a small value, One of the advantages like it provide a code tracking function and desplitting function. That's two important functions. Code tracking function and desplitting function is already been there. Okay, so this dither generator gets the early path and the late path. Okay, and it will compare it out, and this process it makes code tracking. This process, the synchronization being done here. So the code tracking function and the desplitting function been done on this TDL is similar to this previous clock diagram. So the early and the late version is generated. It generates a local generated PN code. Okay, the PN code is driven by a clock signal. You can see that the PN code is driven by a certain clock signal. It's generated by a clock sequence. This clock sequence is phased. Okay, is phased with die tethered back and forth. Okay, with a square law switching function. So what it says like PN code generator as a clock function, internal clock which has a phase. It phase goes with back and forth by using a square law function. So you have a clock here. So there is a phase being deviated. Okay, with respect to some angles, right? So there is a deviation in the phase with respect to the deviation in the clock sequence. So this will eliminate the necessity of identical transfer function of early and late stages. So it will make sure the signal to noise performance SNP, okay, will be around 1.1 dB, uh, uh, which is quite okay with the DLL, which PST which you have seen. So the noise performance should be properly calculated with the proper early path and late path with the proper synchronization of this clock for the PN sequence generator. So this is a looping process. It makes a square detector and gives to this loop. Okay, so it detects the code, and once again it goes to the data output. So here uh, this synchronization, acquisition, and tracking. Mainly, this is being done, okay, for the codes to be retrieved back in a proper sequence. Okay. Uh, someone is talking, you can mute your mic. Okay. So we have finished this unit. So coming to this unit number 5, we have seen this spread spectrum and the multiple axis. So the two different sections is there. One is spread spectrum, one is multiple axis. Either one questions may come. So you can prefer the easiest one is multiple axis, where you have the CDMA, TDMA, FDMA. It's quite easier to understand and learn. Whereas you have come, if you come to this stress spectrum, there you have the PN sequence, okay, M sequence, DSSS, jamming, FHS synchronization tracking. So this unit I can be referred fully in the B. Clark SKLR digital communication book. There is a reference 3. It's quite there, and you can also refer in the textbook to Simon Hackins. So this unit emphasize the codes which is being spread out in an environment, okay, and you use some spreading techniques, DSSS, FHSS, okay, how this spreading techniques been used to retrieve the data properly, and the multiple access in an environment, in a latest mobile and base station, how this link is been established, and how different users can share the same channel. So that is being divided as 1G, 2G, 3G, that is based on FDMA, TDMA, CDMA. So we have finished it, and we will see, we'll have one quiz for some 10 minutes. So as a content beyond the syllabus for the subject, so we'll be having a one-to-one online quiz. I will project the screen. So as per instruction from the your department, so instructed to take over giving some that is a learning methodology should be uh, different based on the flip plus online quiz they are given, and based on some seminars you can able to attend, and some a guest speaker from outside you can call, and we can have one more session on that. If possible, we will have quiz based Google form also. So we have planned to take problem, solve the problem. So we'll have some 3 to 4 session on unit 1 to unit 5. We will try to solve all the uh, university problems. Okay, so you can also note down that important problems, and later on we will have a discussion on the important part A, part B sections. Okay, and part C. So this is teaching methodology. On a teaching methodology, you will have the online quiz. Okay, as of now, one-to-one. So I will just forward. I will just go forward this question, and next you have the answer. You can post the required answer in the chat box. Okay, you can post the required answer. You can put the options also, or else you can unmute and you can also say the answer. Okay, let us start the quiz. So first question. We'll have some 2 minutes for it. You can put in the chat also. A, B, C, D, E. You can put the required answer in the chat. So questions was taken from unit 1 to unit 4. So this is just to revamp your knowledge, and if you have studied, you can answer it. So you can put in the chat box. Request all everyone to attend. Okay, see. Anyone 3 to 4 answers can be taken. Okay, fine. So just to revamp your subject, we are having this quiz. Okay, so C, reduce the bandwidth. Okay, fine. Next one. Okay, very good. You've given the answer, right answer for the second for this question. You can able to put the required answer of the chat. Okay, your answer is B. Okay, in the channel. This the communication system noise affects the signal mostly. You have the most number of noise in the channel. You have AWG and additive voice processing channel. You have white noise. Okay, so you have some external noise, environmental noise also, which will affect. So this will mostly predominant in the channel. Okay, fine. Question number 3. It's a very basic thing. The answer can put. Okay, well, okay, fine. So communication consists of electrical means of dash information given as on the support, right? So let us see. Yes, that's right. So here the basis of communication, sending, processing, and receiving, all these things will be there. Okay, fine. Question number fourth question. So this you have mentioned A. Some of you are given. So amplitude modulation is used for broadcasting because it's compared to other systems. So AM you have studied in, I think it's unit number 1, AM, FM, PM. So let us see it. C is the answer. So it's used to avoid receiver's complexity for broadcasting. With the other system, this amplitude modulation is mainly used to avoid receiver's complexity. Okay, fine. Next question. High intermittent frequency in the super heterodyne receiver. I think we have seen the super heterodyne receiver. It's one of the important topic too in this subject. So what's the C you given? Fine, let us see the answer. So it increases tracking problem. So here you see that the high intermittent frequency in the super and receivers improves stability, selectivity, tracking problem, reduces adjacent channel rejection. Okay, this is mainly used to increase the tracking problem. So as we've seen in our class, like tracking, this word is more similar. So it's also been used in this super internet receiver. It also used in a special type receiver called rake receiver, RAKE. So these receivers are mainly designed particularly for the synchronization and tracking. Difference between the phase and the frequency modulation. I think you can surely give the right answer. Difference between PM and FM. A given. Fine. Many of them are giving A. That's great. So lies in the different modulation index. So it varies with the modulation index value. Okay, fine. Next question is good about quantization noise in a PCM transport modulation system depends upon what are the parameters. Sampling and quantization we have learned. So in a quantization, there is a noise, right? Quantization noise. So this will affect the system. So it depends upon the question number 12. B. Fine. So let us see what's his answer. Okay, B. Number of quantization levels. So here he's given us sampling rate, number of quantization levels. So both these sampling rate and number of quantization levels. So This quantization level has to be properly synchronized, properly designed such a way that unlock the digital conversion. So this sampling and quantizing levels are more important. Okay, so it defines the SNR value. SNR is more higher, your system is more stable and less noise. Okay, question number 15. Which one of the following is not necessarily an advantage over FM or AM? So which one of the following is not necessarily an advantage of FM over AM? So if given as better noise immunity, uh, the for FM it provides better noise immunity, or the power is more aspect power is more useful, and lower the bandwidth is required, or the less modulation power is required. Okay, let's see the answer. Less modulating power is D. So for this previous, which one of the following is more necessarily most of the advantages like less modulating power is required or AM. So that's the D, and D is the answer. Fine. In Q16, the PM, the frequency deviation is in as constant or zero or proportional to modulating frequency or proportional to amplitude of modulating frequency. Okay, we'll see the answer. That is D, that is the proportional to amplitude of modulating signal. Yes, for the in PM, the frequency deviation is proportional to the amplitude of the modulating signal. 20, the television, the vertical synchronization pulse occur every after. So there are some horizontal and vertical synchronization in a television. So it has specific synchronization blocks for vertical and horizontal lines. So we call this scanning lines, horizontal scanning and vertical scanning. So for this T20, it is scan pulses occurs every after field, frame, or scanning lines, or none of them. So there is a frames. Okay, we have some block of frames as well. We have fields, but you have to the scanning lines. So where this does this pulse synchronization occurs? Okay, A. Shrutika is given A. So let's see this frame. Okay, so the elevations are mainly being framed out. So it already have a scan lines. So those lines will be on the display. So every television have this pulse being incorporated in frames. So it has a frame, lot of frames. So one of the frame, if it is not available or not, it's been distorted. So what happens, like at the time you'll see some flicker in the television. Okay, some burst of flickers. Okay, some pops. Okay, some, if you have some grains, it all affects the frames. Fine. 223, equal to quantization noise ratio, the PCF, pulse code module system depends upon. It will be, you can put the answer. Let us see the uh, option output. Okay, answer is B. Number of quantization levels. Okay, the SQN of ratio in the PCM depends upon the number of quantization levels. Since it is already given as signal to quantization. Next one, 225. 100% modulation is produced in AM and carrier is. I think you should have known this. So question number 25, we have the answer as A. Amplitude equals signal amplitudes. Okay. So question number 27, this is very easy. Modulation is the process of. I'm sure you can choose the right answer. So we'll see this question number 29. For a given carrier wave, maximum undistorted power is transmitted when the value of modulation is. You can see the answer. D is 1. So maximum modulated index is the 1. So for a given carrier maximum undistorted power, we will have a maximum modulation as 1. So we will stop the online one-to-one quiz. So next class we will have this problems being solved from unit 1 to 4. We'll say madam and myself will be solving the problem. After that we will have a seminar you can able to take some topic in this platform. Okay, so thank you very much. We have finished up to 5 minutes. We will have we'll try to put each and every problems bank in the GCM as far as possible. Okay, so as we have requested, a lot of students like we need some problems. Um, so we will